Chapter 3, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 3, Part 2. Level Turns. A turn is made by banking the wings in the direction of the desired turn. A specific angle of bank is selected by the pilot, control pressures applied to achieve the desired bank angle, and appropriate control pressures exerted to maintain the desired bank angle once it is established. See Figure 3-5. All four primary controls are used in close coordination when making turns. Their functions are as follows. The ailerons bank the wings and so determine the rate of turn at any given airspeed. The elevator moves the nose of the airplane up or down in relation to the pilot and perpendicular to the wings. Doing that, it both sets the pitch attitude in the turn and pulls the nose of the airplane around the turn. The throttle provides thrust, which may be used for airspeed to tighten the turn. The rudder offsets any yaw effects developed by other controls. The rudder does not turn the airplane. For purposes of this discussion, turns are divided into three classes: shallow turns, medium turns, and steep turns. Shallow turns are those in which the bank, less than approximately 20 degrees, is so shallow that the inherent lateral stability of the plane is acting to level the wings unless some aileron is applied to maintain the bank. Medium turns are those resulting from a degree bank, approximately 20 degrees to 45 degrees, at which the airplane remains at a constant bank. Steep turns are those resulting from a degree of bank, 45 degrees or more, at which the overbanking tendency of an airplane overcomes stability and the bank increases unless aileron is applied to prevent it. Changing the direction of the wings lift toward one side or the other causes the airplane to be pulled in that direction. See Figure 3-6. Applying coordinated aileron and rudder to bank the airplane in the direction of the desired turn does this. When an airplane is flying straight and level, the total lift is acting perpendicular to the wings and to the earth. As the airplane is banked into a turn, the lift then becomes the resultant of two components. One, the vertical lift component, continues to act perpendicular to the earth and opposes gravity. Second, the horizontal lift component, centripetal, acts parallel to the earth's surface and opposes inertia, apparent centrifugal force. These two lift components act at right angles to each other, causing the resultant total lifting force to act perpendicular to the banked wing of the airplane. It is the horizontal lift component that actually turns the airplane, not the rudder. When applying aileron to bank the airplane, the lowered aileron on the rising wing produces a greater drag than the raised aileron on the lowering wing. See Figure 3-7. This increased aileron yaws the plane towards the rising wing, or opposite to the direction of turn. To counteract this adverse yawing moment, rudder pressure must be applied simultaneously with aileron in the desired direction of the turn. This action is required to produce a coordinated turn. After the bank has been established in a medium banked turn, all pressure applied to the ailerons may be relaxed. The airplane will remain at a selected bank with no further tendency to yaw since there is no longer deflection of the ailerons. As a result, pressure may also be relaxed on the rudder pedals, and the rudder allowed to streamline itself with the direction of the slipstream. Rudder pressure maintained after the turn is established will cause the plane to skid to the outside of the turn. If a definite effort is made to center the rudder rather than let it streamline itself to the turn, it is probable that some opposite rudder pressure will be exerted inadvertently. This will force the plane to yaw opposite its turning path, causing the plane to slip to the inside of the turn. The ball in the turn and slip indicator will be displaced off-center whenever the airplane is skidding or slipping sideways. See Figure 3-8. In proper coordinated flight, there is no skidding or slipping. An essential basic airmanship skill is the ability of the pilot to sense or feel any uncoordinated condition, slip or skid, without referring to instrument reference. During this stage of training, the flight instructor should stress the development of this ability and insist on its use to attain perfect coordination in all subsequent training. In all constant altitude, constant airspeed turns, it is necessary to increase the angle of attack of the wing when rolling into the turn by applying up elevator. This is required because part of the vertical lift has been diverted to horizontal lift. Thus, the total lift must be increased to compensate for this loss. To stop the turn, the wings are returned to level flight by the coordinated use of ailerons and rudder applied in the opposite direction. To understand the relationship between airspeed, bank, and radius of turn, it should be noted that the rate of turn at any given true airspeed depends on the horizontal lift component. The horizontal lift component varies in proportion to the amount of bank. Therefore, the rate of turn at a given true airspeed increases as the angle of bank is increased. On the other hand, when a turn is made at a higher true airspeed at a given bank angle, the inertia is greater and the horizontal lift component required for the turn is greater, causing the turning rate to become slower. See Figure 3-9 on next page. Therefore, at a given angle of bank, a higher true airspeed will make the radius of the turn larger because the airplane will be turning at a slower rate. When changing from a shallow bank to a medium bank, the airspeed of the wing on the outside of the turn increases in relation to the inside wing as the radius of turn decreases. The additional lift developed because of this increase in speed of the wing balances the inherent lateral stability of the airplane. At any given airspeed, aileron pressure is not required to maintain the bank. If the bank is allowed to increase from a medium to a steep bank, the radius of turn decreases further. The lift on the outside wing causes the bank to steepen, and opposite aileron is necessary to keep the bank constant. As the radius of the turn becomes smaller, a significant difference develops between the speed of the inside wing and the speed of the outside wing. The wing on the outside of the turn travels a longer circuit than the inside wing, yet both complete their respective circuits in the same length of time. Therefore, the outside wing travels faster than the inside wing, and as a result, it develops more lift. This creates an overbanking tendency that must be controlled by the use of ailerons. See Figure 3-10. Because the outboard wing is developing more lift, it also has more induced drag. This causes a slight slip during steep turns that must be corrected by use of the rudder. Sometimes during early training in steep turns, the nose may be allowed to get excessively low, resulting in a significant loss of altitude. To recover, the pilot should first reduce the angle of bank with coordinated use of rudder and aileron, then raise the nose of the airplane to level flight with the elevator. If recovery from an excessively nose-low steep bank condition is attempted by use of the elevator only, it will cause a steepening of the bank and could result in overstressing the airplane. Normally, small corrections for pitch during steep turns are accomplished with the elevator and the bank is held constant with the ailerons. To establish desired angle of bank, the pilot should use outside visual reference points as well as the bank indicator on the attitude indicator. The best outside reference for establishing the degree of bank is the angle formed by the raised wing of low-wing airplanes, the lowered wing of high-wing airplanes, and the horizon, or the angle made by the top of the engine cowling and the horizon. See Figure 3-11 on page 3-11. Since on most light airplanes the engine cowling is fairly flat, its horizontal angle to the horizon will give some indication of the approximate degree of bank. Also, information obtained from the attitude indicator will show the angle of the wing in relation to the horizon. Information from the turn coordinator, however, will not. The pilot's posture while seated in the airplane is very important, particularly during turns. It will affect the interpretation of outside visual references. At the beginning, the student may lean away from the turn in an attempt to remain upright in relation to the ground rather than ride with the airplane. This should be corrected immediately if the student is to properly learn to use visual references. See Figure 3-12. Parallax error is common among students and experienced pilots. This error is a characteristic of airplanes that have side-by-side seats because the pilot is seated to one side of the longitudinal axis about which the airplane rolls. This makes the nose appear to rise when making a left turn and to descend when making right turns. See Figure 3-13. Beginning students should not use large aileron and rudder applications because this produces a rapid roll rate and allows little time for corrections before the desired bank is reached. Slower, small control displacement, roll rates provide more time to make necessary pitch and bank corrections. As soon as the airplane rolls from the wings level attitude, the nose should also start to move along the horizon, increasing its rate of travel proportionately as the bank is increased. The following variations provide excellent guides. If the nose starts to move before the bank starts, rudder is being applied too soon. If the bank starts before the nose starts turning, or the nose moves in the opposite direction, the rudder is being applied too late. If the nose moves up or down when entering a bank, excessive or insufficient up elevator is being applied. As the desired angle of bank is established, aileron and rudder pressures should be relaxed. This will stop the bank from increasing because the aileron and rudder control surfaces will be neutral in their streamlined position. The up elevator pressure should not be relaxed, but should be held constant to maintain a constant altitude. Throughout the turn, the pilot should cross-check the airspeed indicator, and if the airspeed has decreased more than 5 knots, additional power should be used. The cross-check should also include outside references, altimeter and vertical speed indicator, VSI, which can help determine whether or not the pitch attitude is correct. If gaining or losing altitude, the pitch attitude should be adjusted in relation to the horizon, and then the altimeter and VSI rechecked to determine if altitude is being maintained. During all turns, the aileron, rudder, and elevator are used to correct minor variations in pitch and bank, just as they are in straight and level flight. The rollout from a turn is similar to the roll-in, except the flight controls are applied in the opposite direction. Aileron and rudder are applied in the direction of the rollout or toward the high wing. As the angle of bank decreases, the elevator pressure should be relaxed as necessary to maintain altitude. Since the airplane will continue turning as long as there is any bank, the rollout must be started before reaching the desired heading. The amount of lead required to roll out on the desired heading will depend on the degree of bank used in the turn. Normally, the lead is 1/2 the degrees of bank. For example, if the bank is 30 degrees, lead the rollout by 15 degrees. As the wings become level, the control pressure should be smoothly relaxed so that the controls are neutralized as the plane returns to straight and level flight. As the rollout is being completed, attention should be given to the outside visual references, as well as the attitude and heading indicators to determine that the wings are being leveled and the turn stopped. Instruction in level turns should begin with medium turns so that the student has an opportunity to grasp the fundamentals of turning flight without having to deal with overbanking tendency or the inherent stability of the airplane attempting to level the wings. The instructor should not ask the student to roll the plane from bank to bank, but to change its attitude from level to bank, bank to level, and so on with slight pause at the termination of each phase. This pause allows the airplane to free itself from the effects of any misuse of the controls and assures the correct start for the next turn. During those exercises, the idea of control forces rather than movement should be emphasized by pointing out the resistance of the controls to varying forces applied to them. The beginning student should be encouraged to use the rudder freely. Skidding in this phase indicates positive control use and may be easily corrected later. The use of too little rudder or rudder use in the wrong direction at this stage of training, on the other hand, indicates a lack of proper conception of coordination. In practicing turns, the action of the airplane's nose will show any error in coordination of the controls. Often during the entry or recovery from a bank, the nose will describe a vertical arc above or below the horizon and then remain in proper position after the bank is established. This is the result of a lack of timing and coordination of forces on the elevator and rudder controls during entry and recovery. It indicates that the student has knowledge of correct turns, but the entry and recovery techniques are in error. Because the elevator and ailerons are on one control and pressures on both are executed simultaneously, the beginning pilot is often apt to continue pressure on one of these unintentionally when force on the other only is intended. This is particularly true in left-hand turns because the position of the hands makes correct movement slightly awkward at first. This is sometimes responsible for the habit of climbing slightly in right-hand turns and diving slightly in left-hand turns. This results from many factors, including the unequal rudder pressures required to the right and to the left when turning, due to the torque effect. The tendency to climb in right-hand turns and descend in left-hand turns is also prevalent in airplanes using side-by-side cockpit steering. In this case, it is due to the pilots being seated to one side of their longitudinal axis about which the airplane rolls. This makes the nose appear to rise during a correctly executed left turn and to descend during a correctly executed right turn. An attempt to keep the nose on the same apparent level will cause climbing in right turns and diving in left turns. Excellent coordination and timing of all the controls in turning requires much practice. It is essential that this coordination be developed because it is the very basis of this fundamental flight maneuver. If the body is properly relaxed, it will act as a pendulum and may be swayed by any force acting on it. During a skid, it will be swayed away from the turn, and during a slip, toward the inside of the turn. The same effects will be noted in tendencies to slide on the seat. As the feel of the flying develops, the properly directed student will become highly sensitive to this last tendency and will be able to detect the presence of, or even the approach of, a slip or skid long before any other indication is present. Common errors in the performance of level turns are failure to adequately clear the area before beginning the turn, attempting to execute the turn solely by instrument reference, attempting to sit up straight in relation to the ground during a turn rather than riding with the airplane, insufficient feel for the airplane as evidenced by the inability to detect slips or skids without reference to flight instruments, attempting to maintain a constant bank angle by referencing the cant of the airplane's nose, fixating on the nose reference while excluding wingtip reference, ground shyness, making flat turns, skidding, while operating at low altitudes in a conscious or subconscious effort to avoid banking close to the ground, holding rudder in a turn, gaining proficiency in turns in only one direction, usually the left. Failure to coordinate the use of throttle with other controls, altitude gain lost during the turn. Climbs and climbing turns. When an airplane enters a climb, it changes its flight path from level flight to an inclined plane or climb attitude. In a climb, weight no longer acts in the direction perpendicular to the flight path. It acts in a rearward direction. This causes an increase in total drag requiring an increase in thrust, power, to balance the forces An airplane can only sustain a climb angle when there is sufficient thrust to offset increased drag. Therefore, climb is limited by the thrust available. Like other maneuvers, climbs should be performed using outside visual references and flight instruments. It is important that the pilot know the engine power settings and pitch attitudes that will produce the following conditions of climb. Normal climb. Normal climb is performed at an airspeed recommended by the airplane manufacturer. Normal climb speed is generally somewhat higher than the airplane's best rate of climb. The additional airspeed provides better engine cooling, easier control, and better visibility over the nose. Normal climb is sometimes referred to as cruise climb. Complex or high-performance airplanes may have a specified cruise climb in addition to normal climb. Best rate of climb. Best rate of climb, VY, is performed at an airspeed where the most excess power is available over that required for level flight. This condition of climb will produce the most gain in altitude in the least amount of time. Maximum rate of climb in feet per minute. The best rate of climb made at full allowable power is a maximum climb. It must be fully understood that attempts to obtain more climb performance than the airplane is capable of by increasing pitch attitude will result in a decrease in the rate of altitude gained. Best angle of climb. The best angle of climb, Vx, is performed at an airspeed that will produce the most altitude gained in a given distance. Best angle of climb, airspeed, Vx, is considerably lower than the best rate of climb, Vy, and is the airspeed where most excess thrust is available over that required for level flight. The best angle of climb will result in a steeper climb path, although the airplane will take longer to reach the same altitude than it would at best rate of climb. The best angle of climb, therefore, is used in clearing obstacles after takeoff. See Figure 3-14. It should be noted that, as altitude increases, the speed for best angle of climb increases, and the speed for the best rate of climb decreases. The point at which these two speeds meet is the absolute ceiling of the airplane. See Figure 3-15 on next page. A straight climb is entered by greatly increasing pitch attitude to a predetermined level using back elevator pressure and simultaneously increasing engine power to the climb power setting. Due to an increase in the downwash over the horizontal stabilizer as power is applied, the airplane's nose will tend to immediately begin to rise of its own accord to an attitude higher than that at which it would stabilize. The pilot must be prepared for this. As a climb is started, the airspeed will gradually diminish. This reduction in airspeed is gradual because of the initial momentum of the airplane. The thrust required to maintain straight and level flight at a given airspeed is not sufficient to maintain the same airspeed in a climb. Climbing flight requires more power than flying level because of the increased drag caused by the gravity acting rearward. Therefore, power must be advanced to a higher power setting to offset the increased drag. The propeller effects at climb power are a primary factor. This is because airspeed is significantly lower than at cruising speed, and the airplane's angle of attack is significantly greater. Under these conditions, torque and asymmetrical loading of the propeller will cause the airplane to roll and yaw to the left. To counteract this, the right rudder must be used. During the early practice of climbs and climbing turns, this may make coordination of the controls seem awkward. Left climbing turn, holding right rudder. But after a little practice, this correction for propeller effects will become instinctive. Trim is also a very important consideration during a climb. After the climb has been established, the airplane should be trimmed to relieve all pressures from the flight controls. If changes are made in the pitch attitude, power, or airspeed, the airplane should be retrimmed in order to relieve control pressures. When performing a climb, the power should be advanced to the climb power recommended by the manufacturer. If the airplane is equipped with a controllable pitch propeller, it will have not only an engine tachometer, but also a manifold pressure gauge. Normally, the flaps and landing gear, if retractable, should be in retracted position to reduce drag. As the airplane gains altitude during the climb, the manifold pressure gauge, if equipped, will indicate a loss of manifold pressure, power. This is because the same volume of air going into the engine's induction system gradually decreases in density as altitude increases. When the volume of air in the manifold decreases, it causes a loss of power. This will occur at a rate of approximately 1 inch of manifold pressure for every 1,000-foot gain in altitude. During prolonged climbs, the throttle must be continually advanced if constant power is to be maintained. To enter the climb, simultaneously advance the throttle and apply back elevator pressure to raise the nose of the airplane to the proper position in relation to the horizon. As the powers increase, the airplane's nose will rise due to increased download on the stabilizer. This is caused by increased slipstream. As the pitch attitude increases and the airspeed decreases, progressively more right rudder must be applied to compensate for propeller effects and to hold a constant heading. After the climb is established, back elevator pressure must be maintained to keep the pitch attitude constant. As the airspeed decreases, the elevators will try to return to their neutral or streamline position, and the airplane's nose will tend to lower. Nose-up elevator trim should be used to compensate for this so that the pitch attitude can be maintained without holding back elevator pressure. Throughout the climb, since the power is fixed at the climb power setting, the airspeed is controlled by the use of elevator. A cross-check of airspeed indicator, attitude indicator, and the position of the airplane's nose in relation to the horizon will determine if the pitch attitude is correct. At the same time, a constant heading should be held with the wings level if a straight climb is being performed, or a constant angle of bank and rate of turn if the climbing turn is being performed. See Figure 3-16. To return to straight and level flight from a climb, it is necessary to initiate the level off at approximately 10% of the rate of climb. For example, if the airplane is climbing at 500 feet per minute, FPM, leveling off should start 50 feet below the desired altitude. The nose must be lowered gradually, because a loss of altitude will result if the pitch attitude is changed to a level flight position without allowing the airspeed to increase proportionately. After the airplane is established in level flight at constant altitude, climb power should be retained temporarily so that the airplane will accelerate to the cruise airspeed more rapidly. When the speed reaches the desired cruise speed, the throttle setting and the propeller control, if equipped, should be set to the cruise power setting and the airplane trimmed. After allowing time for engine temperatures to stabilize, adjust the mixture control as required. In the performance of climbing turns, the following factors should be considered. With a constant power setting, the same pitch attitude and airspeed cannot be maintained in a bank as in the straight climb due to the increase in the total lift required. The degree of bank should not be too steep. A steep bank significantly decreases the rate of climb. The bank should always remain constant. It is necessary to maintain a constant airspeed and constant rate of turn in both right and left turns. The coordination of all flight controls is a primary factor. At a constant power setting, the airplane will climb at a slightly shallower climb angle because some of the lift is being used to turn the plane. Attention should be diverted from fixation on the airplane's nose and divided equally among inside and outside references. There are two ways to establish a climbing turn. Either establish a straight climb and then turn, or enter the climb and turn simultaneously. Climbing turns should be used when climbing to a local practice area. Climbing turns allow better visual scanning, and it is easier for other pilots to see a turning aircraft. In any turn, the loss of vertical lift and increased induced drag due to the increased angle of attack becomes greater as the angle of bank is increased, so shallow turns should be used to maintain an efficient rate of climb. All factors that affect a plane during level flight, constant altitude, turns will affect it during climbing turns or any other training maneuver. It will be noted that because of the low airspeed, aileron drag, adverse yaw, will have a more prominent effect than it did in straight and level flight, and more rudder pressure will have to be blended with aileron pressure to keep the airplane in coordinated flight during changes in bank angle. Additional elevator back pressure and trim will also have to be used to compensate for centrifugal force, for the loss of vertical lift, and to keep pitch attitude constant. During climbing turns, as in any turn, the loss of vertical lift and induced drag due to the increased angle of attack becomes greater as the angle of bank is increased, so shallow turns should be used to maintain an efficient rate of climb. If a medium or steep bank turn is used, climb performance will be degraded. Common errors in performance of climbs and climbing turns are attempting to establish climb pitch attitude by referencing the airspeed indicator, resulting in chasing the airspeed. Applying elevator pressure too aggressively, resulting in excessive climb angle. Applying elevator pressure too aggressively during level off, resulting in negative G forces. Inadequate or inappropriate rudder pressure during climbing turns. Allowing the plane to yaw in straight climbs, usually due to an inadequate right rudder pressure. Fixation on the nose during straight climbs, resulting in climbing with one wing low. Failure to initiate climbing turn properly with the use of rudder and elevators, resulting in little turn, but rather a climb with one wing low. Improper coordination resulting in a slip, which counteracts the effects of a climb, resulting in little or no altitude gain. Inability to keep pitch and bank attitude constant during climbing turns. Attempting to exceed the airplane's climb capability. End Chapter 3, Part 2. Recording by Dale Latham.